if I now add my Hartree-Fock energy, which is W1 plus W2, that's my Hartree-Fock energy, plus this second order correction, what I get here, this is what is called the MP2 energy. So Møller-Plesset perturbation theory, second order energy is the Hartree-Fock energy plus this energy correction. So that's MP2, which is the cheapest correlated wave function way of getting a correction to the Hartree-Fock energy. It's the cheapest one because it's the double excitations which are the only ones who directly contribute. I mean, if there would be a single excitation, that would be cheaper because there are few of them, but it's double excitation. So what's the cost of this energy correction? Well, I have a sum over I, J, A, and B. And normally, I mean, you write that 1 over 4 and remove those restrictions. And the concern about I and J equal the same and A and B equal the same, there's again, this minus sign removes that term. So that's a sum over 4 index, 4 orbital index. So that scales as n to the 4th power, n being the number of orbitals. So the cheapest energy correction is in principle scaling to the 4th power of the number of basis functions. However, these are integrals in the molecular orbital basis. These are the Hartree-Fock orbitals. And in order to get those, we have to do that integral transformation, which I was shortly talking about last week, where I mentioned that this is a process n to the 5th power. So although the energy correction is actually only n to the 4th power, in order to be able to calculate it, meaning getting the integrals, you have to do this n to the 5th power step for the integral transformation. So the lowest energy correction for the correlation energy correction you can get is n to the 5th power. Now, MP2 is the first one. The next step would be including a third order correction. That would be called MP3. By the way, MP2 gives you typically 80 to 90% of the correlation energy. All the Møller-Plesset methods, MP2, 3, 4, whatever, they are not variational. We didn't optimize the wave function by going for the lowest energy. We used this projection technique in order to get the wave function coefficients. So this is not a variational method, which means you certainly can come below the exact energy. But compared to, for example, CI singles doubles, which is sort of the competitor from the CI world that also includes the doubles, this method is actually size extensive. It scales correctly with the size of the system. So that problem, remember the hydrogen 2 dimer in infinite distance, where if I would calculate the energy of the dimer, it wouldn't be twice the energy of the monomer. This does not happen for MP2. If you do an MP2 calculation on the dimer, you get twice the energy of the monomer. And that actually means that if you're doing chemistry, size extensivity is so much more important than whether it's a variational method. I mean, variation is nice, but it's only nice if you're only interested in the lowest energy state, in the absolute energy of the lowest state. And who is interested in the absolute energy of a state? You're interested in reaction energies, if you're interested in reactions, but that's the difference between two energies already. And there your variation principle is gone. You only can say this one is the lowest and this one is the lowest, but if you don't know whether they're equally low, you know nothing about what the energy difference is. So the variation principle is nice for an exact for an absolute energy at one point. But typically we're interested in energy differences. We're interested either in reaction energies or excitation energies, and that's differences, so we can't use anything. So, very short, MP3, that's including the W3, the third order energy correction. And remembering that we have the 2n+1 rule, for the third order energy correction, we also still only have the same wave function, so we still only have double excitations included. So that's only also only IJAB, like this. That then could give 90 to 95%, 95% of the correlation energy. MP4 then, there you need the second order wave function. You need second order wave function. And that has singles, doubles, triples, and quadruple excitations. So this is very much more expensive to do that. And it is actually nowadays no longer used. There was a period in the history of quantum chemistry, computational chemistry, where you saw a lot of Møller Plesset MP4 calculations. Sometimes without the triples. They actually, for technical reason, they are more expensive than the quadruples here. So you would see MP4 singles, doubles, quadruples, and then some people could do singles, doubles, triples, and quadruples. But that's in a way all history. Also, even MP3 is history, because nowadays one does MP2 because that's the cheapest one. And if you want to have something better, more expensive, you go directly to coupled cluster. And we're going to discuss on Thursday what that actually means. That actually means this one.